Hello again. Alright, this lesson is about stateful sets. So now that we looked into persistent volumes and have been using persistent volumes and persistent volume claims together with pods, it's important to talk about stateful sets, because pod isn't the recommended way. Pods aren't the recommended way to use persistent volumes. And there are several reasons for that, which we'll just scratch at the surface. But the stateful set is a particular structure. Can you remember that when we created a replica set, that the pods of the replica set, similar to the jobs or the pods of a job, that they have random names? And that means that the identity of the pod is random, where there are labels that show their belonging to a superior object, a job or replica set. But whenever the container fails, a new container will be created, and the new container will have a different identity, a different name, a different IP address. And now imagine you want to create a cluster, a database cluster, where you have 3 nodes, and the 3 nodes, they need to find each other. Then a unreliable network identity isn't what we want. We have seen services, and they provide a stable network identity. And we will see that in the example of stateful sets, we use a so-called headless service to provide a stable identity for the pods of the stateful set. But there's a special behavior for stateful sets in contrast to the behavior of replica sets and deployments, which is that the pods of the replica set, they have a very defined name, and they are starting with 1 or 0, and to be precise. And so all the pods have numbers assigned to them, and this forms a strong identity of each pod in the stateful set, which means that if pod number 1 will fail, a new pod number 1 will be created, not a pod number 573, for example. And we will also see that this is important because the pod identity also correlates and implies a stable network identity, which is necessary for the discovery of the pods within a stateful set, which is required during forming a cluster data service. I think we won't get so far to create a cluster data service, but we'll look into the features of the stateful set, and we'll create a simple Postgres pod to show you the abilities of the stateful set. In a stateful set, there's a strict ordinality, which isn't the case in a replica set. So the pods are created in a strict sequence ordinality, which means pod number 1 is created before pod number 2. I think they start with 0, so pod number 0 is created before pod number 1, created before pod number 2. If you apply certain lifecycle operations, for example, scaling up, scaling down, or updating, this sequence will always be kept. So you'll scale up pod number 1, pod number 2, pod number 3. If you scale down, it's the other way around: pod number 3, pod number 2, pod number 1, respectively pod number 2, pod number 1, pod number 0. For some operations with data services, ordinality is a requirement. I don't think we'll have vivid examples for this, but there are those operations with those requirements, and the stateful set is therefore superior to the usage of replica sets because you have more control. One feature of the stateful sets in conjunction with the pod identities is very important. The stateful set, similar to a replica set, can also specify a number of pods. So you could say that I want to have 3 replicas. Similar to a replica set, you can specify a pod template that will be then instantiated 3 times. Now, the interesting difference is that you can also specify a persistent volume claim template because you want to have 3 different persistent volume claims. This means that if you create a 3-node stateful set, each pod will have its own identity and a one-to-one, a reliable, stable one-to-one relation to a particular persistent volume claim, and therefore to a particular persistent volume. This means that the disk of pod number 0 will always be the disk of pod number 0. And this is very important because in a Postgres cluster, for example, you could have a asynchronous streaming replication with leader election. This means that you'll have a primary database, also called a master, or formerly known as a master, and secondaries, formerly known as slaves, where the master is the one that receives all the write requests and distributes its state by replicating to the streams, by streaming replication to the secondaries. Well, this is a push or a pull, doesn't really matter. The point is there's the leader with the most recent data, and you always need to specify who is the leader, and you need to ensure that write requests are exclusively going to the primary. And this means that if the primary fails, you want to reattach the data of the failed primary during resurrection. So we've seen that in Kubernetes, and in if the image of a container is cached, the restart of a container can happen within seconds. So think about your master Postgres being stressed. Somehow the Postgres, maybe because of a bug in the program in Postgres itself, it collapsed. Kubernetes recognizes it and within a few seconds restarts the database. You want to ensure that it has back the latest version of the persistent disk. We're not talking about the possibilities that the file system could be corrupted or that there could be data inconsistencies during such a failure, which could always be happen. But assuming that this is not the case, the fact that one node will get one particular disk is very, very important. So this alone, the pod identity, the network identity with this headless, using a headless service, together with the persistent volume claim templates and the one-to-one assignment of persistent volumes to a particular pod, makes the stateful set the sole option when it comes to data service automation in Kubernetes. Never use a deployment, never use a replica set unless you are more an expert than me and know something that I don't know, which is possible. Alright, so pod identity and persistent volumes are stable network identities.